Hi, I'm Apur from the Robotics and Biology Lab at the Technical University of Berlin. I'm presenting my paper that outlines fundamental principles that enable simultaneous design of hardware and control of manipulation systems. But before getting to that, let's first try to understand why should we be co-designing the hardware and control of our robots. So let's look at the field of hardware design. I think roboticists have come up with very clever mechanisms, materials, and overall designs of grippers. Few of them are shown here, where some form of mechanical intelligence is encoded within the hardware to generate interesting robot behavior. On the other side, there's also considerable effort in designing the control strategies, usually using general purpose anthropomorphic hands, where the aim is to encode some form of computational intelligence in our robots through our control strategies. However, I think as designers, we should be able to encode as much intelligence in either the hardware or the control, depending on our task. But we have to be very careful here, because there's quite a strong correlation between the chosen hardware and the required control strategy. So for example, when you take an anthropomorphic hand and a suction gripper, you require very different control strategies for a simple task, let's say, of picking up a book from a table. So there is significant synergy that must be ensured while we are designing the hardware and control. And I think we can ensure this synergy by simultaneously co-designing them. And to enable this co-design, I think we should think about fundamental principles like the ones that exist for the isolated fields of hardware or control design, and that's what we aim to do in this paper. So what do we need for co-design? The first step is we need to define some search space that is spanned by hardware and control parameters. Now, instead of moving along the X or Y axis of the search space, as we were doing if we were doing isolated hand design or control design, we can move in any directions within our co-design problem. And now, how do we get to the best possible hardware and control combination in our co-design space? Well, the simple strategy is maybe just to initialize at a lot of points and evaluate the performance at each point. But there's a problem in that, and I will show you the problem with a simple example. Let's consider this robot hand that's grasping this tall blue object in its palm. So the task is of static grasping, so there is no dimension of time. Even for a simple task, the co-design problem can be very challenging because the search space is reasonably high dimensional. So each finger of the hand actually contains 20 parameters. The parameters for one of the finger is shown here. It has 15 hardware and 5 control parameters. And we have 4 such fingers. So this is an 80-dimensional search space. And the bigger problem is that a lot of the volume of the search space doesn't contain reasonable co-design. So let's look at some of the designs within the search space. So here we have some designs which have fingers pointing in very random directions, fingers all around the palm. One design on the bottom right actually contains fingers of 0 length. And all of these designs actually are not good at the task of grasping the blue object. So most of the volume of our search space actually contains task irrelevant designs. Therefore, our strategy of sampling and finding the best solution might not be the most efficient one. So instead, why don't we just initialize at certain point and just move to the locally better co-design in the space? And by that, I just mean follow the local gradient, but the question is the gradient of what? To understand that, we also have to consider another aspect of our problem that we haven't touched upon till now, is that our robots are operating in some environment. And usually in case of manipulation, they are manipulating some part of the environment. So I think we should consider that in the co-design problem. And I think the interaction with the environment encodes all the information needed for structuring the co-design space. And and getting the local gradients for improvements in our hardware and control. So assuming we have that gradient, we can just follow the local gradient to reach a locally optimal codesign. Just to linger on this a bit, to understand this gradient, let's analyze the gradient along the x-axis first. This blue gradient actually maps the changes in robot motions to the changes in control parameters and is of course known as the robot Jacobian. And that is something that we all study about in our fundamental robotics courses. Similarly, we formulate an augmented Jacobian that describes the changes in robot motion with changes in both its hardware and control parameters. And with this Jacobian, we have everything that we need to co-design the hand for grasping that I described earlier. So we start with defining the environment. So we start with the palm and the blue object in the palm. We initialize at a point in the third space where the finger lengths are 0. Well, the first step is defining some physical constraints or the interaction I want this robot to do. And then here it's just described with these 4 contact points in red. And then we can just use the codesign Jacobian. And now you can see how the optimization progresses, which leads to our final hand design. So using this approach, we co-design diverse manipulation systems like robot arms, grippers, and multi-fingered hands for simple tasks. And in the process, we understand the structure of the co-design space for manipulation and exploit that structure using the codesign Jacobian. I would finally like to thank all the funding agencies that enable our research, and thank you for listening.